How do you send an email to Mars when the message takes 20 minutes to travel one way, and the planet itself might disappear behind the sun for 2 weeks? The internet as we know it would shatter. So, how does NASA talk to its robots millions of miles away? The problem is threefold: massive delays, frequent disruptions from things like solar flares or planetary alignments, and no continuous end-to-end connection. The solution is a revolutionary concept called Disruption-Tolerant Networking, or DTN. Think of it less like a real-time phone call and more like a cosmic postal service. At its core is the store and forward principle. Each node in the network acts as a post office, holding on to a data packet until it has a clear, confirmed connection to the next node. This isn't random. DTN uses a contact graph to predict when satellites and planets will be in the right position, scheduling these data handoffs minutes, days, or even weeks in advance. To prevent data loss, it uses custody transfer. The receiving node must confirm it has received the data intact before the sending node is permitted to delete its local copy. The key software governing this is the bundle protocol. It takes our data and wraps it in a protective shell called a bundle, designed for the harsh realities of space travel. This bundle contains crucial metadata like the ultimate destination, the source, and a lifetime timer so the packet knows when to self-destruct if it can't be delivered. For each individual hop, DTN often uses the Licklider Transmission Protocol, or LTP. It ensures all the data makes it reliably from one node to its immediate neighbor. So, the bundle protocol manages the entire journey from Earth to Mars, while LTP handles the short point-to-point hops between satellites along the way. And what about security? The bundle protocol security specification, or BeepSec, provides authentication and encryption, creating a secure shell for our interplanetary messages. DTN is also adaptable, using convergence layers to work over any communication link, whether it's a traditional radio signal or a next-generation laser beam. This isn't just theory. DTN is already being used on the International Space Station and is a core component of NASA's Artemis missions to the Moon. But it's not just about clever software. DTN requires incredibly robust and specialized hardware designed to survive in the vacuum of space. Processors must be radiation-hardened. Cosmic rays and charged particles can flip bits in normal chips, causing catastrophic failures. Rad-hardened chips are built to resist this. Because nodes have to store data for long periods, they need high-capacity, reliable solid-state storage that can operate flawlessly in extreme temperatures and vacuum. Instead of fixed radios, modern spacecraft use software-defined radios. These can be reprogrammed in flight to change frequencies, data rates, and even entire protocols on the fly. To be heard across millions of miles, nodes use high-gain antennas. These massive dishes focus radio energy into a pencil-thin beam, concentrating all the power towards the target. The next leap is laser communications. Optical terminals can transmit data at rates 10 to 100 times higher than radio, using less power and mass. And none of this works without power. Reliable energy sources, from massive solar arrays to radioisotope thermoelectric generators, are the lifeblood of every deep space node. Tying it all together are the onboard DTN routers, the brains of the operation, running the bundle protocol on that rad-hardened hardware, making autonomous routing decisions. DTN isn't a magic bullet for speed, however. The latency, the light speed travel time, is a hard limit. DTN manages disruptions. It can't break the laws of physics. A major challenge is standardization. For a true interplanetary internet, all space agencies and private companies must agree to use compatible hardware and protocols. And then there's scalability. How do you manage a network that grows from a few dozen nodes today to thousands of satellites, bases, and spacecraft throughout the solar system? The ultimate goal is a seamless interplanetary internet, where a scientist on Earth can transparently access data from an instrument on a moon of Jupiter, just as they would a server on Earth. In the future, artificial intelligence will play a huge role, dynamically optimizing data routes based on predicted solar weather and network traffic, making the system even more resilient. And on the far horizon, technologies like quantum communication could one day offer instantaneous, unhackable links, changing the rules of space communication entirely. So, disruption-tolerant networking, with its store and forward protocols and rugged hardware, is the foundational architecture for our multi-planetary future. It's the invisible nervous system that will connect explorers on the moon, rovers on Mars, and probes in the outer solar system, enabling the next great age of discovery.